Good afternoon, Professor.
Good
Good
afternoon.
afternoon, Professor.
Good afternoon. Good afternoon. Well done. Well done. On more than one count. Good afternoon. Oh, wow. The squares just switched. So I think that was good. Good afternoon, Caroline. Good afternoon. I think that was Amy. I'm not, it goes so fast, but okay. Good afternoon, guys. Thank you very much. Well, and good afternoon, Caitlin, and good afternoon, Caroline. Good afternoon, Amanda. Good afternoon, Kevin. Good afternoon, Shamil. Good afternoon, Liz.
Good afternoon, Professor.
Good afternoon, Savannah. Okay, that I saw. That's awesome. Oh, my board. Goodbye, my board. That just keeps leaving. All right. Hold on. And good afternoon, David K. Hi, Christina. Good afternoon, Kevin. Good afternoon, Jamalette. Good afternoon, Chloe. Good afternoon, Sophia. Good afternoon, David. Good afternoon, Amanda. Good afternoon, Kimberly. Good afternoon. Wow, this is a full house, as it should be. But good. Good afternoon, Liz. Good afternoon, Adon. Good afternoon, Dave. Good with a C. Good afternoon, Caitlin. Good afternoon, Amy. Good afternoon, Shamil. Okay, awesome. Good afternoon, my board again. I don't know why. All right, so congratulations. First of all, I think I'm saying that to everybody here. Wait a minute, I think I am actually saying that to just about it. Well, I am saying congratulations to everybody here. I know this test, I got a lot of communication. Like during the weekend, during today, mostly during the weekend, and there was a lot of so I know this test was not a joke for anybody. Well, I think for most people it was not a joke. I think you worked hard. I think it took over some little chapter of your lives for a little while, and took over some mental space for a little while. I think everybody rallied. I mean, so they've all just come in. Of course, I don't have numbers or anything like that. Maybe some of you don't even want the numbers yet. I don't know. I don't have numbers or anything. They just came in. We're going to move on in a minute, at least temporarily. You will get back numbers. We'll talk about that. But I want to say that if you're, I'm pretty sure, and I'm checking back and forth as I'm saying this to make sure, because I know some people had challenges of different kinds and challenges from other areas of life. And there was a mistake in the first problem, which didn't help anybody. And I hope you got that notification late last night. And that notification applied to whether you had already turned in the test or not. What I'm saying is, I think it was not a joke weekend for anybody, nor for my electronic board that keeps falling off. But if you are here right now, here's the thing. Pretty much, if you are here right now, you either have turned in you've either turned in a test, which you are to be congratulated no matter what's on it, or you communicated with me and we're in a conversation about a situation. And so that's good if you communicated. That's largely true for everybody in this room. And in any case, if you're in this room now, you're in this room now, which was part of the arrangement and part of the hope and expectation. And it's definitely noticed if you're in the room right now, like more than usual. I think it takes something to show up after something like this for a lot of reasons. So anyway, I don't want to dwell, and I do want to get my board working. And one of the reasons you're in the room now is so that we can move on with new material and introduce new material that's a little bit harder to catch up if you miss it. I mean, everything is catch upable, but I want everybody to see the connection to the new material here and move on. But really, the main thing is, I want to say right now, no matter what you think you did, if you did something on this exam, you are to be congratulated. You should breathe out for a little bit. You should know that you did the hard part, which is doing it. And you're not going to get numbers back on Wednesday. That's impossible for a couple of reasons, not the least of which is that there are some situations in the room. I will hope to get it back for you for the next class for Monday. I'm hoping. I'll give you more of an update on that on Wednesday, but you when you get numbers back, we'll talk about the numbers and we'll put them in context. But everybody's still standing in this class. I'm going to say this now, and I'm going to say it when you get the numbers back. Nobody has written their own. I don't mean this morbidly, but there's nothing that anybody has done in this class yet that they can't come back from, or that means that they failed or something like that. That has not happened to anybody yet. I just want to make that clear. Everybody's in different places, perhaps, and I'm very impressed with you overall as a group. But even if you in your heart are listening right now and you're like, yeah, I don't think he's talking to me because I'm totally messing up this class or something like that, which I know some of you feel because I started hearing that this weekend. Like, I know there are people in the room that feel like, uh-oh, I've totally lost grip of this class and now I'm realizing it, whatever. I'm just here to say my three least favorite words in the English language, honestly, my three least favorite words in the English language are, it's too late. And my least six favorite words are, and I'm talking about when they're applied to me, I can't stand hearing it's too late, and I can't stand hearing it's too late, you messed up. Like as in irrevocably. So don't feel that way wherever you are. There's things that can happen still in this class for everybody. And hopefully for some people or maybe hopefully for a lot of people, that means there's still things that can happen to ensure an A. But even if it's not an A, like, nobody is dead in the water yet. I'm just, okay. And if this midterm provided an opportunity for some of you to think that maybe you should have an individual conference with me and like really talk about some stuff, physics or life, or how they're conflicting for you right now, then good. Okay, then good. So then let's take that opportunity. But all right. But I'm psyched that you're all here. I'm psyched that all of you who are here. It means a lot. It is noticed. And I'm turning on my board again, or trying to turn on my board again. I'll tell you right now. So we're going to turn to totally new material now, material that is kind of at the heart of physics. You've been exposed to it in the lab already, which is the way it worked in real life. Like, people started seeing the following ideas in the lab before they started really putting them in mathematical or written down terms. So the material that we're going to now is Newton's laws. And by the way, stop me again if you have any questions now that the tests are in, most of them. If you have, let me know if you have any questions, but that I mean questions about the implications of the test. Like, if there's questions about your particular exam or even particular questions, I might have to hold those until sort of I have all of them and all of them come back. But if you want to be reminded at any moment, like how the grades work or anything like that, you put it in the chat. Even if I don't answer it right now, I will. I do understand that tests suddenly elevate everybody's consciousness of what's going on in a class. So that may have happened, but or elevate. Anyway, all right. So here's the deal with the new material. So here's the new material. Okay, so this is a lot. Sorry, that's a lot of writing. I'll read my handwriting out loud I'll read it out loud to make sure you can follow my handwriting, and then I'm going to explain what this is about. So what we're going to do today is hopefully, I'm going to lay out all three of Newton's laws today in one class. So it's just three laws, but in a way that's a lot of information for one class, but that's what we're going to try to do. And again, you've seen some of this being introduced already in labs. So, and of course, by the way, I totally know that you've heard of these things before in like 6th grade and high school and things like that, but hopefully this will be a new and more refined and perhaps more mathematically helpful perspective. Hang on one second. Hang on one second. Okay. So, all right. So background. So Galileo is our man. And remember, everything we've done so far, really, in one way or another, is some version or implication of this principle of relativity that comes from Galileo. Galileo works from 1580s to 1642, and he's the developer, not the inventor, but the developer or a developer of the telescope. Certainly one of the first people ever, if not the first, to use a telescope to look to the heavens and draw what he sees. And from that start to really take very seriously and publish in various ways arguments and perspectives and writings about the idea, about taking very seriously the idea that the Earth really could be viewed as moving past the sun as opposed to the other way around. And he gets into a lot of trouble for that idea, as I think you know. But the real idea that the Earth could be moving while we don't feel it. There was my board again. That real idea is an idea that ends up being not just about the Earth, but about how everything moves in general, both off Earth and on Earth. And this whole way of thinking about motion, this way is called the principle of relativity. And remember, just to back on again, I'm going to put the board back on again. Just remember, I keep calling it the principle of relativity, and we keep saying that we have these different forms: form 1, form 2, form 3, form 4, form 5. They're all different ways of saying this principle, but they're not. But they are all one principle and they're a principle in the sense that they tell us how the laws of physics are going to unfold. When they unfold, it is not a law of physics, it is a law of how physics laws will be written or understood. It's a very deep idea. I mean, he literally says the laws of physics will be the same in all unaccelerated frames of reference. And as he's saying that, we know that he knew that he didn't know what those laws would be. He hadn't written the laws of physics yet, but he was saying whatever they will be, they've got to follow this law of laws. It's a very kind of amazing way to start a science. Again, let me just remind you that it's like the fact that there are laws in New York City, perhaps, that tell you what you can and cannot do. And maybe there's even laws in New York State that tell you what you can and cannot do. But there's a law of laws called the United States Constitution, which actually dictates how the laws of New York State can or cannot be written, right? I mean, you know this, right? So we have laws that are deeper than laws. That's what oh, cool. Oh, okay, cool. Okay, cool, direct chat person. Okay. And that's what Galileo's principle is, okay? It's a law of how the physics laws are going to be, how they're going to work and how they're going to be applied. And that principle is ultimately relativity. Says that physics is all about motion through space and time. Our key notion of motion is velocity. And the principle of relativity says velocity, that idea, does not apply to one object at a time. It always applies to pairs of objects. It's always a comparative relational idea. It's a relation between two objects, not a property of one, right? That's Galileo's idea. Now, then Galileo dies in 1642. I'm starting the board again, sorry. And in Christmas, or thereabouts, the documentation is a little bit controversial, but basically around Christmas of 1642, of the year of Galileo's death, Newton, in a totally other country, and I'm not saying they knew each other or anything, I'm just saying the torch gets passed to Newton, who's born in England, and starts publishing an amazing amount of thick material, some of which he keeps in very small circles, and some of it gets distributed to wider circles. And the big book, I'm just trying to get my board to go, the big book that he publishes, where he puts together all these fundamental principles of math and physics, kind of in the style of Aristotle almost. I'm just trying to get my board back. It's called the Principia Mathematica. And there's a lot in the Principia. It's a very dense, very groundbreaking text. It's not, the idea is that it's just laying out all the fundamentals of this new natural science, which is going to become known as physics, or this new natural philosophy, I should say. But in there, not right at the beginning, but in there are these laws of motion. Okay, so now this is now in the late 17th century, the late 1600s. We have laws of motion getting published. Again, Galileo had published a lot and had done a lot to change, to sort of give birth to the whole idea of experimental physics and astronomical physics and so forth. But now Newton lays down actual laws, as Galileo had sort of suggested would eventually happen. I'm going to, okay. Come on, okay. And there are three laws. I mean, there's a law of gravity. There's a lot going on in this book, and there's definitions and all this, but there's three fundamental laws of motion, from which everything else about motion is supposedly going to follow. And we're gonna talk about them right now. Again, I just want to remind you, though, and they are the cornerstone of physics to this day. These three laws of motion, everything in physics sort of like spokes off of these three laws. If you're wondering why we take so long to get to these laws, if they're so fundamental, because my belief is that what's even more fundamental than the laws are two things: definitions of the terms that the laws refer to. And believe me, Newton takes a long time dealing with definitions in his book before he ever gets to laws. So all of kinematics and all the stuff that you just got tested on in a weird way really is on definitions of motion. And in a way, that's why it's abstract and difficult to people often, because we're trying to establish for the first time what we even mean when we ask these questions about velocity, acceleration, displacement, etc. But then also, what's really fundamental to how the laws work, what ties them all together, is this principle of relativity. So here's what, and Newton knew that. Galileo knew that laws were coming. Newton knew that the laws that he developed would have to come from what Galileo had said. It is a dialogue over history that we are a part of, without a question in my mind. So, and I think you'll see what I mean when I now read you the first law, which of course I know you've heard before. I know you've heard in high school, maybe in lab, in 6th grade, but please write it down in these words anyway. And no, Newton was British, but he didn't write this book in English. Anyway, the book is written in Latin. So no matter what we do is a translation of sorts, but I think these are pretty good words to capture the first law. So the first law, like Roman number 1 here says, sorry, so I never did read. So my handwriting says in 1642, Galileo died on Christmas. In 1642, Galileo died. On Christmas of 1642, Newton was born. He later published Principia Mathematica. In it, we find laws of motion. We find 3 of them. So here's the first one. Unless acted on by a net external force, that says external. Unless acted on by a net external force, an object at rest remains at rest, and an object in motion remains in motion at the same speed in the same direction, right? That's what it says. Hang on one more. Okay. Again, I know you've heard that before, and you've probably heard it said different ways. This is not the only way to say it. I think it's one of the better ways to say it. Let's just get straight a couple of things. First of all, so this law sort of has 3 parts. The first part of the law is giving you a condition under which the law is meant to operate, right? It's setting a constraint or a restriction on the province, the domain of discourse in which the law is meant to govern. So we're saying first, unless acted on by a net external force. Now, let me start. Hold on. Okay. So the first law says, unless we're talking about objects now. Now, the real word that we're going to start using for an object is mass. Like by the time we get to the second law, we're going to, instead of referring to an object as an object, we're going to refer to it as a mass. But by object, we mean, like, I should almost say like maybe I will. Maybe I'll say on the next page. But an object is a discrete, countable, identifiable, possibly tangible object. I mean, entity that can be distinguished from other entities. Okay, that's what a thing, in other words. So we first say in the law that unless acted on by a net external force, an object, blah, 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 blah. So we're about to make a statement about objects. Before we make the statement about objects, we make it clear what kind of objects we're talking about and what we're not. We say, all right, we're about to say something about objects, but we don't mean objects that are being acted on by net external forces. This law is only going to apply to objects that are not acted on by net external forces. Now, what do we mean? So what do we mean by net external force? I'm giving you some provisional definitions here. When I say provisional, I mean working definitions that Newton may have, to some extent, expected that we sort of had in our head, even as we were reading the book, or may have defined a little bit earlier in the book in some cases. But in any case, these definitions are going to get refined more and more as we proceed through the study of physics. Like we're going to get, as we get used to what we're talking about, more and more detailed definitions of these in life, whether it's in this class or not. But the basic working idea of these words that Newton would assume that his readers would have, and that we will have, is that when we say, so we say net external force, by net, we mean sum of. When we say net, we mean add up. So a net force would be the sum of a bunch of forces acting. Okay, and I'm going to tell you right now that from here on in physics, whenever we say net anything like net force, we mean add up a bunch of things and take into account direction. So whatever force is, and we're about to start discussing forces, obviously, force, I'm assuming right from the get-go, might well be a vector quantity. I'm assuming that a force, whatever it is, could act in one direction or another, and i.e. could be designated positive or negative, so that when we add up a bunch of forces, we're going to take into account minus signs. There might be negative numbers in there, but we're still going to add them all up. So net means the sum of a bunch of things, taking into account minus signs if there are any. Okay, that's what net means. External means from the outside. From outside a particular object. If the object is a baseball, it means outside that baseball. If the object is a whole system, like of baseballs on a baseball field, then the object is then the system is the baseball field. We mean another field or something outside that field. So external means from outside the object, specifically meaning some other object. And this is where it starts getting, I think, interesting. So a second object. A force, as you would think in casual English, presumably, a force is an influence. Like a force is like an action. A force is something I do to something else. It's not something I have. It's an influence. It's a way that one object influences another object. Specifically now, if we're saying that it comes from the outside, if this whole condition of this law is asking us to imagine, so a net external force, what I'm trying to say, a net external force is the resulting influence that comes from outside an object, that comes from another object. And if a force is an influence that some second object bears on some first object, and this really is important, if a force is something that a second object does to a first object, or a first object does to a second object. But I'm saying a force is something that one object does to another object. So a really good word for force really is interaction. A force, and in fact, that's like the best word for force throughout physics. A force is an interaction, meaning an activity or an event, an influence between two objects. Inter meaning between, right? So before I go, so the most concrete way to picture it in your mind, it may not sound scientific or rigorous, but the most concrete way to picture what a force is a push or a pull. Specifically, a force is one object. If we say a force is present, we're saying that one object is pushing or pulling another object. Bottom line, a force is not something ever that any one object ever has. It's not like Star Wars in that regard. And I mean, yeah, I love Star Wars, but a force is not something that you possess or have. It's not like temperature. Force is something that you do to another object. You exert. So a baseball bat exerts. Oh, cool. Oh, cool. Okay, hold on one second. I got it. Okay, cool. Okay. Right. So like a baseball does not have a force. Like seriously, like it doesn't, you can't ever say that it does in physics. It doesn't make any sense to say that it does. You can't do, but you can say that a baseball bat exerts a force on a baseball, or a baseball exerts a force on a baseball bat, or whatever. A lightsaber, like a lightsaber doesn't actually have a force, but a lightsaber can hit or something. A lightsaber can exert a force on a Jedi. If that, okay, like it's a force, in other words, is more like a verb, more like, in fact, a transitive verb than it is like an adjective or noun. Now, like, that's a very loose analogy that may lose, like maybe you hate grammar. I don't know. And it's probably not even really a right analogy, but I'm saying you never have a force. You do a force to something else. Okay, now this may start sounding familiar. Why am I making a big point of this? I'm saying right away that forces are interactions between pairs of objects. They're not properties of single objects. Maybe sounds familiar, right? Now I'm going to go further and say, okay, so Newton comes up and says, now, sometimes objects interact with other objects, and we're going to talk about that. Sometimes one object comes along and exerts a force on another object. But first, before we get into that, Newton says, we're going to picture a scenario where that's not happening. Like the beginning of law 1 says, unless acted on by a net external force. So the beginning of law 1 is saying, here's a domain. Let's first think about objects that are not being acted on from the outside. So in short, or in long, really, I'm saying, hold on. So okay, so just to make it absolutely clear, and again, believe me, I know that you know all this in a way, but you may or may not have thought of it this way. We'll see. Newton's first law. See, there's going to be 3 laws. They're going to tell us how objects are expected to move, and they're going to ultimately help us do math and make quantitative, rigorous predictions about how objects move through space and time. So the way it begins, what Newton's saying is, all right, let's begin with how they would move in the simplest possible scenario, how they would move like as though in the control of an experiment, how they would move in the base state. He begins with, like, in other words, before we get into how objects move in response to influences, let's look at an uninfluenced object. Let's first look at what an object would do if left entirely alone by itself, an isolated object in space, right? So it's like a base state. And he says, so hopefully tell me if you need me to move back in the board, but so I'm saying Newton's first law is like a base state. It's how objects would move if as little as possible is happening, if as little details are added to their description as possible. In other words, if it's just one object by itself, what would it do in the absence of influence from other objects? And what we say is, so now I'm putting symbolically what he said in English. He's saying there's two cases. Wait. Like this is a really simple law in a way. And again, I know you've heard it a million times, probably, but in a way, the structure of this law is kind of rich and robust. Like there's a condition and then there's two cases, right? The condition is we're just talking about an object by itself, okay? And we're trying to wipe the slate clean and see like how things would move just in the simplest possible scenario. So the simplest possible scenario is we got an object by itself in space. Okay, that's our condition. Now we divide into two cases. The two cases are case A, you walk in to see this object, like you start your stopwatch, you start looking, you put down a ruler, you're looking at the side, and when you walk in, at the moment that you happen to look at the object, in case A, it happens to be sitting still, right? That's case A. The object happens to be sitting still when you come in to investigate it. At moment zero, like at t equals 0, what do you find? In case A, you find that at t equals 0, the instantaneous is 0. Case B is you walk in and the object already has a velocity, right? You start your stopwatch, you start your investigation, you put down your ruler, and the object is already having, like even before you began, already having some speed in some direction. That's case B, right? Case A is instantaneous velocity is 0, initial. Wait, sorry. Right, that's what I mean. So case A, the initial velocity is 0. Case B, the initial velocity is something other than 0. Just call it V0. So case A, Newton says, all right, if it's case A, you walk in, the thing's not moving, it's going to continue to be not moving forever. An object at rest will stay at rest as long as there are no external influences on the object, right? And case B is an object at rest. Case B is an object that's already not at rest, that's already moving. And there, Newton says that object will continue to be moving forever at the same speed and in the same direction. Like velocity is a vector. I'm putting the vector symbols over it. So he's saying in the case where the initial velocity is not 0, but just called something like V0, then V will remain forever V0, like not 0. So these sound like two different cases. I mean, they are two apparently different cases. One is the object is initially at rest. The other is the object is initially moving. And let me get it really straight now. They're divided into two cases for a reason. Because one of the cases, it sounds like a very obvious conclusion, one that almost doesn't need to be said at all. And the other one is a conclusion that is so not obvious that it actually almost always sounds wrong to people when they hear it, or they just dismiss it, or they figure they're not understanding something or something. Let's get it straight. And again, I'm sure that many of you have thought this through in some way or another, like in 6th grade when you first heard this. But case A says an object at rest will stay at rest. Most people agree with that. And Aristotle like 2,000 years, or like 2,000 years before this writing, made it clear in his writings that he absolutely believed that if a coffee cup is sitting on the table when you walk in, you walk in and you see a coffee cup sitting on the table, you would expect that the coffee cup will continue to sit on the table. You expect that it won't spontaneously start moving in any direction. So I think nobody's surprised by that. But case B says that if an object is in motion and it's not acted on by a net external force, it will continue to stay in motion at the same speed in the same direction, i.e. in a straight line. Now, this is the one that, again, let's pause on this for a minute. I imagine that some of you have thought about this before and maybe even object. I would imagine, okay, so all right, so what are we saying here? We're saying that that the natural state of an object is to continue going at constant velocity, not to slow down, not to stop. That if you leave objects alone, they'll just keep going forever, as opposed to slow down or stop. Now, I don't know where you are in your thoughts on that. But let's just dwell there for a moment. I imagine that when you first heard this in middle school or something, you or your class might have gone through something like, wait, what? Like even, and hopefully you did. Hopefully for a moment, you might have been like, wait, what? I mean, like objects naturally slow down, right? Like that's why we have to put gas in the car. That's right, because cars. Sorry. That's why we have to put gas in the car. That's why we have an oil crisis all the time. Like things don't naturally keep going. Things naturally run down, right? You might, again, one might very reasonably think like, and it takes me, like, I don't naturally, well, forget about me, but like, yeah, cars are, like a rock, you throw a rock on the ground. It rolls for a while, maybe it moves for a while, then it hits the ground, maybe it rolls for a while, but eventually it slows down and stops. That's the world we live in, it seems. In the world we live in, it seems like, at first glance, if left alone, objects naturally, eventually slow down and stop. They don't naturally maintain their own speed. Now, we have to dwell on this for a minute, because you're not crazy. If you ever thought, even if you've worked this all out, and even if you know what you think the resolution is, I want you to remember like the one moment you had in 6th grade when you might have objected to this or were confused by it or whatever, because I do want you to know that for thousands of years, people absolutely remained in that state of mind. Like Aristotle absolutely also wrote as a law that objects naturally slow down to rest. And I mean, he wrote it differently, but in Aristotle's physics, in like 300 BC, the idea was that objects naturally do slow down and come to rest, because that's what we seem to think that we see a lot of the time around us. So what's going on here? What Noon is saying here is, I know it seems like there's two cases. It seems like there's objects that are already at rest that just stay at rest like that. And then there's objects that are in motion. And it seems like the objects in motion tend to slow down to come eventually to rest. But that's not the case, is what Galileo's saying, as you may remember. Galileo's saying, hold on, notice how serious my condition is. My condition is that I'm talking about isolated objects by themselves. I'm not actually yet talking about rocks on the ground. I'm not talking about car tires on the ground. I'm not talking about car tires touching the ground. I'm not talking about rocks being touched by the ground. I'm talking about objects by themselves. In other words, I'm talking about objects, like what he's saying and what you may have told yourself correctly in 6th grade or 7th grade is, hang on, in the world, there's lots of, in the world that we look around, there's lots of objects interacting with each other all the time, often rubbing and sliding against each other, often and exerting forces on each other while they rub and slide against each other. And we often call that force of sliding or rubbing, we often call it friction, but it doesn't, and there's a lot of friction in the world, And it doesn't matter if you like the word friction or you use a different word or whatever. What Galileo is saying is, hang on, right now I'm talking about just rocks by themselves. Once you put a rock on a ground, the ground is going to rub against it. And sure, the ground might do something that I'll get into in the future in the next laws, where the ground might be exerting some kind of pulling or pushing force on the rock that slows it down to rest eventually. But what I'm saying here, but that's an object interacting with another object, is what Galileo is saying. And you might say, and I'm sure many of you came to that conclusion. In other words, in 6th grade or 7th grade, when you hear this and you hear objects in motion stay in motion, but it doesn't seem that way in the real world, what you might tell yourself is, well, right, because, okay, he means in the absence of friction. And he does. He means in the absence of friction. He means an object by itself without rubbing against another object. And it does, but here's why I have to talk about this for so long, I think. If you're with me and you remember in 6th grade or high school saying to yourself, okay, yeah, object in motion stays in motion, but he means like an object without friction. And so obviously he's not really talking about my world. Okay. You can do that and you can say that, and that's fine. But then the problem is, if you're anything like me or a lot of other people, then what you do in your mind is you say, so these laws aren't really about the real world. He's talking about some imaginary, hypothetical, ideal, infinite thing that is like, fine, that's fascinating, but that's not really like the world. And so he can say whatever he wants to say, but I thought he was going to talk about actual motion in the actual world, and apparently he's not. So I don't really have to take this that seriously. It's some abstract ideal, you could say. I'm not saying you said that. I'm saying I said it in my mind. I'm saying my Zoom connection is terrible and we may lose the internet in a moment. I don't know what's going on. But I want to caution you. The reason I'm spending so much time on this now is say, wait, this law does say in the absence of, yes, it's saying in the absence of friction. It does say unless acted on by a net external force. But I don't want you to think that therefore this law is just about some ideal world that never exists. This law is the base case. This law is the control, so to speak, of the experiment that we will start running with the other laws. This law is what happens to a hockey puck if it's on ice that's so smooth that the ice barely exerts any friction on it. Or it's about a hockey puck or a satellite that blasts off into outer space where there's no atmosphere and no air. Now, first of all, we do send things to outer space. That is actually real. But I don't even care about that. I'm saying what this law says is, if you put this law it's not a removed abstraction from the real world. It's the simplest possible version of the real world on which we're going to build more and more realistic details. Put another way, what this law says is, if you put a hockey puck down on really, really rough, like not like black, I mean, the opposite of black ice. Like if you put a really rough hockey puck on the ground and you slap it with a hockey stick, the hockey puck will go a certain amount of distance before it slows down and comes to rest. Now you smooth down that pavement surface that you did, like smooth down, make it black tar or something like that, and slap the hockey puck again with the same conditions. The hockey puck's going to go farther. Now smooth it down even more, and the hockey puck's going to go even farther. Make it ice now, but kind of like rough ice or whatever. It's going to go even farther. Now put a Zamboni, clean up the ice, make the ice super smooth. It's going to go really far. In other words, what this is talking about the limit of a trend here. It's saying, notice that what it's saying is you may not in your lab ever get the ice so smooth that the hockey puck would go infinitely far. You might, with your finite practices in your finite lab space, in your finite ice cleaners, you might only get this puck to go super, super, super incredibly far rather than infinitely far. But what you need to notice while you're doing that, what you need to notice is that the more you get rid of the friction, the farther the puck goes. The more you get rid of the friction, the less the puck decelerates, right? So what you got to notice while you're doing that is that the reason the puck is slowing down is the friction, not anything about the puck. That's the important thing, okay? And this experiment is doable, actually. I mean, you can actually, especially with outer space and stuff. But my point is, even if all you can test with this in your real world is the trend that it's describing, the important takeaway is that single objects don't slow themselves down. Single objects do not naturally slow down, nor do they naturally change direction. What this is saying is that an object left up to its own devices, an object by itself, will not change its velocity spontaneously. Now, here we go. Here comes the hook. What this is really saying is what look like two cases to us, the case of the object that we walked in on while it was still versus the case of the object that we walked in on while it was already moving. What this law is really saying is, okay, I'm going to address both of these cases because I know they seem different to everybody. Every reasoning person, not just every sixth grader who's naive, but every reasoning person, including Aristotle, views these two situations, the object at rest versus the object at motion, as two different cases. And they think the object at rest like stays at rest, and they think the object in motion will eventually come to rest. But they've got it backwards. What you've got to realize, everybody, is these two seemingly different cases are both just cases of an object having some kind of velocity. In one case, the velocity happens to be the number 0. And in the other case, the velocity happens not to be the number 0. But in each case, we have an object with velocity. And what Newton is saying is what is common to both cases. They're both velocities. I don't care whether one has the velocity 0. They're both velocities. And in both cases, what that object will do when left to its own device is maintain constant velocity. He's saying what's true of objects, period, is that objects by themselves do not spontaneously change their velocity. And what he's really saying now, he's saying if you thought those two cases were different until my law, if you thought objects that were at rest would stay at rest, but objects that were in motion would eventually come to rest, if you even intuitively thought that or sort of thought that or thought like that was the real world, then what you were thinking is that the velocity of 0 was somehow special, that objects that already had arrived at 0 would stay at 0, and objects that hadn't yet gotten to 0 eventually had to get to 0. What you're intuitively thinking is that what's linked between the two cases is that in general, the natural state of an object is to get to 0. And that's why you think we have an oil crisis and we need to put gas in the car, or why it takes energy to get out of bed to go to class in the morning, because you're intuitively thinking that all objects want to eventually want to be at 0 velocity, that 0 velocity is somehow a special number for isolated single objects. But what what Newton's really saying is this. What's really powerful about this law that kicks off Newtonian physics, what Newton's saying here is 0 is not a special velocity. Like objects do not want to come to 0. The object that's already at 0 is not at some special state that the object which is moving wants to get toward. 0 is not a special velocity for any one single object because no single isolated object has a velocity. All objects are going 0 relative to themselves. No object is going 0 relative to another object. No object is ever going 0 relative to another object. I mean, unless they're the same, unless it is. But all objects are going 0 relative to themselves. all velocities are relations between pairs of objects. Zero. So what I'm really trying to say is, if I'm looking at an object and I say that object's at rest, well, what I really mean is that object is at rest relative to me, right? If I'm running past that object, then the object is not at rest anymore, right? No object is actually at rest. No object is by itself going at velocity 0. So it couldn't possibly be the case that objects are trying by themselves to be at velocity 0. In other words, this is Galileo. What I'm really saying is, I'm really saying this is the 6th form of Galileo's principle of relativity. What we now know as Newton's first law is really the 6th formulation of Galileo's principle of relativity. What we're really saying is all objects want to do the same thing, which is maintain their velocity, whatever their velocity is. I don't care whether it's 0 or not. Objects want to maintain their velocity. And then if someone comes along and says, well, wait, really? I mean, you're saying all velocities are like interchangeable, like there's nothing special about sitting at rest. Objects don't want to sit at rest. What I say is, but no object is sitting at rest. Last way I'm going to put this, and I'm going to move on. But what I'm trying to say is this law is a way of this first law is really just Galileo's principle turned into law form. And if you really understand Galileo's principle, you really take it seriously. If you take seriously the idea that even the Earth is not at rest, even the ground below our feet is going 65,000 miles past the sun, and that doesn't bother anybody, and it's totally natural, and it's the natural state of affairs all the time, that sort of tends to suggest objects do not naturally want to sit still. Even the Earth is not sitting still. More to the point, I don't know what sitting still means. What I'm really trying to say is, if you believe, here's this coffee cup sitting on my desk, right? So you walk in, you see this coffee cup sitting on my desk, and you're like, that coffee cup's going to stay there. This is the first part of the law. I understand. Case A, that coffee cup is going to stay there. It's not going to spontaneously just hook left, right? And I'm like, right, I agree. It would be crazy if this coffee cup just spontaneously hooked left. It's not going to spontaneously develop some new velocity that it didn't have before. Objects don't spontaneously accelerate, is what we're saying, right? But then, if you really believe that, like, start running past the coffee cup, right? Start running past the coffee cup. You run past the coffee cup at a constant velocity and just watch the coffee cup while you're running. Now, from your frame of reference, the coffee cup is not sitting still. It's moving, right? And you would be shocked if you kept on running. If you kept on running at the constant velocity and you were watching that coffee cup, so now the coffee cup is going the other way at constant velocity, you'd be shocked if that coffee cup spontaneously suddenly grinded to a halt and stopped, because that would mean that it had spontaneously built up velocity and started catching up with you, right? Like, you would not, in other words, something that is moving, if it's really isolated, if friction's not involved, you would be shocked to see it spontaneously slow down or turn left or speed up. They're all as insane as each other. What you expect is that objects maintain a constant velocity, whatever that velocity is, and we don't specify whether it's 0 or some other number, because whatever the velocity is just a matter of what frame of reference you're in the first place. Objects don't have velocities. They only bear velocities compared to whatever's observing them. So, I'm getting a little carried away here, but I'm saying the first law of physics says, of Newton, says objects, what it says, in short, it says, and we'll move on, in absence, isolated from other objects, if an object is by itself and not interacting, no matter what the situation is, the velocity of an object will stay whatever it was. Objects do not. Isolated objects do not spontaneously accelerate. It's not that objects won't move by themselves. It's that objects won't change the way they're moving by themselves. That's what the law says, okay? And really all this is is Galileo's principle, and this is the sixth form of it. If you really understand that all velocities are relations, then you'll understand that if we believe that objects at rest stay at rest, then we have to believe objects at constant velocity, at some velocity, will stay at constant velocity, because there's no difference between one velocity and another. It's all a matter of reference frame. Okay, that's law one. I'm just laying it out for what it's worth. That's law one. So all of law one says the base case is objects left alone don't accelerate. So then law two gets us into, okay, well, what if they are influenced by a net external force? Then what happens? And the answer is they do accelerate. And here's law two. Law two is mathematical. Oops, sorry. This is law two. Okay, of course, you've heard this before too. The rest of our lives is about this law in a way. We're gonna spend, in a way, the rest of the course is about unpacking and doing math, solving problems from this law. So let me just quickly identify the parts. I write it as sigma F equals ma. The sigma means sum of. So some people write F net, same thing. So sum of means net, taking into account directions. And F means force, A means acceleration, M means mass. So I mean, in largest terms, what we're saying here is from now on, what we're saying is, okay, if a mass is subjected to some forces, if a mass is influenced by other objects, one or many, then the object will accelerate. It will change its velocity. The first law we established the opposite. Like, if not, then not. If a mass is not subjected to forces, then it will not accelerate. Its A will be zero. So if net F is zero, then A is zero. But if there is some aggregate amount of influences acting on a mass, then the mass will accelerate accordingly. And in fact, what we're saying here, as you can tell, is this is, thank goodness, there's no squares or cubes or cube roots or anything like that in this law. It's a linear equation. It's literally F net equals ma. So we are saying that the rate at which a mass accelerates is directly proportional to the extent to which it's been forced. So the greater you push a mass, the greater it will accelerate. And And now remember a couple of things I'm trying to say on the sheet here. First of all, acceleration is a vector, right? Acceleration means change in velocity per time, and velocity is a vector. It includes speed, magnitude, and direction. So an object can, so to accelerate is to change velocity. That could mean to speed up, it could mean to slow down, or it could mean to turn, to change direction. Force is also a vector. Force also has direction. So if you push an object in a certain direction, it will accelerate in that direction. Or if you pull it in another direction, it'll accelerate in another direction. Specifically, force and acceleration are both vectors. So really, to say that F net equals ma is really to say independently and simultaneously along the x-axis, all of the so along one axis, all of the forces acting on that axis in one direction minus all the forces acting in another direction, accelerate the mass accordingly along that axis. If there's a bunch of northward pointing forces that are really strong, minus a couple of southward pointing forces that are really weak, all acting on some mass, then the mass will accelerate to the north at a certain rate. But simultaneously, yet independently, that's happening on this axis and on that axis, okay? It's real. So if we live in three-dimensional space, then F net equals ma is really three simultaneous but independent equations. Okay. I should do, we're almost, okay. From here on in, acceleration, is measured in meters per second squared. Mass is measured in kilograms. 1 kilogram of mass times 1 meters per second squared of acceleration from now on is going to be known as 1 Newton of force. Okay, force is measured in units called newtons. A Newton is a kilogram of mass times a meter per second squared of acceleration. So in other words, a Newton of force is how much force it takes for me to take a kilogram and bring it from like to pull up, like say an apple is like say a kilogram in mass. If I take a big apple, if I take an apple and I pull it up and I bring it from rest to 1 meter per second squared if I bring it from rest to 1 meter per second of velocity in 1 second, let's say, and 1 meter per second of velocity is about 2.25 miles per hour. So I take this apple and I get it from nothing, from rest to 2.25 miles per hour in a second. However hard I had to push to do that or pull to do that, that's a Newton of force. Okay. We have to say a lot more about this law, but since there's a lot more, I mean, this is the computational law. We'll solve all of our problems with this law. But again, it's like the converse of law one. Law one is if nothing's happening to you, then what you're not necessarily going to sit still. but you're not going to change your velocity. If you're not being influenced, then you will maintain constant velocity, right? You can't accelerate without influence. Then law number 2 says, okay, the sum of all the influences on something along a particular axis will yield the acceleration of that object along that axis. Okay, that's what it's saying. Force is directly proportional to acceleration and inversely proportional to mass. We'll say a lot more about it, but that's the second law. So finally, the third law, and we'll end with this. The third law it's kind of, so the third law is English again. And sometimes I wish the third law were the first law, because the first law says what's happening in the base case, like when no force is acting. The second law says what will occur if a force is acting or many forces are acting. And the third law really finally actually tells us how to picture or what we really mean by a force in the first place. The third law is this, and I know you've heard it many other ways. Please write this way down. We're going to end with this, but I think it's going to sound clunky to you, but I think it's really important to know this version of the law. Okay, I'm going to read it. I'm going to give, there's 2 more minutes. I think I'm going to do one more page just to write something about this, one fast page. But here's the law. You've heard it as action reaction. You'll see why this is, I think, a more specific, rigorous way to say action reaction. It says, if object A exerts a force on object B, then object B exerts a force on object A of precisely equal magnitude in precisely the opposite direction. Okay, so it's saying that what we mean when people say action reaction, what they mean is if I push you, then you push me in exactly the opposite direction with exactly the same strength. If I push you, you push me back. And by the way, I shouldn't even say the word back because it's not even a time delay. If I push you, then at the same time, necessarily, you're pushing me with the same strength. Got it. Got
Even
it.
if you leave.
Oh, okay. Got it. Okay. Okay. So if I push you, you push me. And it doesn't matter who made the decision, doesn't matter who started. If I push you, you push me with the same strength in the opposite direction. The last thing I'm going to say about, and that's as opposed to a lot of things that a lot of people think, but i.e., a force is a symmetric interaction between 2 objects. That's what a force is. It is a symmetric interaction between 2 objects. It's not possible for me to pull you without you pulling me. And if I pull you with 30 newtons of force, you pull me with 30 newtons of force. So this is, oh, and by the way, that is, sorry, this is it. That's just GPR again, but now number. It's just saying a force is an interaction between a pair. It's a matter of framework. If I think I pulled you, you pulled me. Like literally, I married my wife on October 20th, 2012. Guess what? My wife married me on October 20th, 2012. Duh. That's just the nature of marriage, right? Same thing with forces. It's just that a force is a symmetric pull or push. That's it. I know I've gone over time. You've been great. Thank you for being so patient. I know it was a rough day. Get some sleep or get some relaxation. I'll see you on, there's no new homework other than just a game turn. I'll see you on Wednesday. Have a great day. I'm turning off the recording.
Have a good day, Professor.
Have a great day, Professor.
Bye, Professor.
Bye. Okay. So wait, I'm turning off the recording. Hang